Hello, I'm Tim Lindquist, and this is SER 321, Principles of Distributed Software Systems. And today I want to talk about, we're going to cover reflection, which is the first part of the class notes section on threading. So this is Unit 10. And there are some referenced readings in both of the textbooks. That material actually covers in Chapter 3 and Chapter 7 of Java Network Programming and Java Network Programming and Distributed Computing. That material covers threading, and before we talk about threading, I want to look at runtime environments in a little bit more detail, or at least give you a model for a runtime environment, pretty much for the Java runtime environment. And that actually is covered on the overheads, class notes on concurrency, threads, and synchronization. So let's take a look at that. So the first section is motivation for threading, and I'm not going to talk too much about it because I think it's pretty clear. If you're working in a browser and you want the browser to be downloading a file at the same time you're clicking on links and doing other stuff, there has to be some threads working in the background or within the browser in order to enable that to work. Exact same thing in what we're going to do with the media library or media browser, and that is you're going to be able to download an MP3 or an MP4 file from the server from your Raspberry Pi, and you want the user to still be able to select different media and do other things like that while in the background it's getting ready to play. So that's the idea behind looking at threading. It's a very important part of distributed applications. Some of the frameworks that we're going to look at, that we have looked at, RMI and JSON RPC, on the server side, it already takes care of threading for us. But on the client side, it's a different story. So here are the outcomes for this section, and that has to do with identifying when threading is important. Also, the difference between using a thread and real concurrency. Concurrency meaning things are actually happening in parallel. And then also the ability to do it in Java. So java-lang.thread and java-lang.runnable. And then describe the information and organization of the Java runtime environment. That's what we're going to take a look at today. Actually, the first three that I just described are the things that we'll do in the next unit. And then the Java Reflection API, along with an understanding of the Java runtime environment. You'll see that the Java Reflection API is very, very clearly an important part of it. So there are references to the exact same sections out of the textbooks, and here are some other materials. So in the Java tutorial, there's a section that is very good and worth looking at. And then you don't worry about C#. Here are the example programs. So let's talk about the execution context, right? So the idea is that we have a program running, and that's typically an operating system implemented in the context of a process. And what we want to be able to allow happen is to have multiple activities, if you will, or threads going on in that process at the same time or within that executing program. So here's a diagram that I picked up from I'm not sure where that kind of shows you within a given executing program two different sequences of execution, separate sequences of executions. So they may be both of these threads may be executing the exact same code, or they may even be accessing the same object, calling methods on that object, or even accessing public fields on the object. But in fact, they're separate. They're independent of each other, meaning that we don't know the relationship between the time that the second instruction, each of these little boxes intended to be an instruction, you can think of it as a statement in the programming language, We don't know the relationship between the time this instruction is executed and this instruction is executed, right? One may be in front of the other, before the other, and one may be after the other. And a multi-core processor on a multi-core processor, they may both be at the exact same time. So the idea behind threading is that there's an independence. We know that we have two things that we want to get done, and let's set them both to work, and whichever one goes first goes first. Well, I think it's worthwhile looking at a general model of a runtime environment, kind of a high level instead of the gory details of it, in order to understand better the notion of threading. So here are at the highest level the basic components of a runtime environment for an object-oriented language such as Java. So the first thing is called an activation stack. And the activation stack is exactly that's a stack. We push things onto the stack and we pop things off of the stack. But the information that we push onto the stack may be different sized. All right, so the blocks of information or the information that goes onto the stack may vary considerably in their size from one push to another push. And I think the other thing to associate it with is that a push is associated with calling a method, and a pop is associated with returning from a method. And the idea is that all of the local variables, not class instance variables, but all of the local variables within a method, those things that are defined, if I define an int inside a method, it actually is in C++ we call it automatic storage, but it is allocated as part of that stack frame. All right, so a stack contains an entry or a frame for each active method in the program. So if method A calls method B and method B calls method C, then in fact we will push onto the stack a frame for method A, and then on top of it will be another frame for B, and another frame for C, and another frame for D, and then if D returns, then that frame for D will be popped off, and so forth. So the stack actually grows and shrinks in terms of the frames that are on it. And the information on in each frame includes all of the local variables for that particular frame. So this is the notion of an activation stack. It tells us the current level of nesting of method calls at any given point in time. And the importance for threading is that the stack may contain frames for different threads, and they may be intermixed. So there's a mechanism built into the activation stack to relate different frames on that stack based upon the thread that they exist. And it's not necessary to have a separate stack for each thread. A single data environment or a single runtime environment may be used by multiple threads. So the next notion is that of a code cell, and the code cell is exactly the instructions itself. All right, so when you write a Java program and use the javac command to compile it, it gets converted into a .class file. Now, that .class file, among other things, includes code cells, and code cells are the translation of the Java instructions. So an if statement would be represented probably by several different code cells within it. The Java bytecode is a stack-based bytecode. That's not the same. It's not the same stack as the activation stack, but it presumes that there exists a stack in terms of its execution. So in fact, it's using a separate. The code, the bytecode itself is stack-based code. And then there's another storage area called heap storage. So code cells exist someplace and they're identifiable in terms of what method they belong to and so forth. Then there's heap storage, and heap storage is in Java, it's the garbage collected storage. All right, it is where objects are created. Java is different than C++ in that in C++ we can actually create objects, instances of classes, and put them on the stack, and that's called automatic storage. or we can create an instance of an object and we can put it on the heap in C++. And in C++, if you see a new operator, then you know it's heap-based storage as opposed to automatic. And in Java, it's always, that's the only way we can create the instance of an object is either through a special initialization, a factory method, or by means of the new method. Either way, we end up creating it on the heap. So this is where objects are stored, created, accessed, deallocated, and garbage collected. Each time an object is created, a reference to it is placed on either the stack, meaning the activation stack, or within another object of the heap. All right, and that's actually kind of an important thing to understand. So if I have a if I have a method, and inside that method I create a local, I have a new, I create, so for example, group, my group is a new group impl, then that group, the new group impl goes onto the heap, right? The new group impl object gets created in the heap, but on the runtime stack is a reference to it, a pointer to it. All right, so in fact, every accessible object in the heap has some kind of a reference to it, and that reference is anchored on the runtime stack, on the activation stack. Sometimes I say activation stack, sometimes runtime stack, they both mean the same thing. And then there's also on the heap, well, it doesn't necessarily have to be on the heap, but generally it is, a class storage. All right, so Java has this thing called a reflection API, and that reflection API is where they're at runtime is a manifestation of every class that has been loaded. And in Java, there's this notion of a class loader, and that class loader brings in classes and builds an internal representation of that class, as well as checking the code that goes along with that class, right? So it's literally loading the .class file, and loading that .class file means building these code cells, or at least finding out, having a runtime representation of those code cells, as well as information about the class itself, reflective information about the class on the heap. And that reflective information about the class is all centered with a thing called a class called class. All right, so here is the notion of a class loader. The reality is you can write your own class loader, and there are a couple of predefined class loaders that Java runtime environments use. One class loader is used to load what are called the base classes, boot classes, not base, boot classes, called the boot class loader. And in, I'll show it to you here, and in most Java runtime environments, Java commands, it starts out by loading all of the classes in the using the boot class loader. Let me show you what I mean. There is a So on Linux, I mentioned before there are several. There's a default JDK that comes in with Debian Wheezy, and it turns out that the directory for it is userlib JVM, and actually, if you do take a look at userlib JVM. You can see there are multiple on this particular, so this is Wheezy. There are multiple Java virtual machines. The one that is the active one is this Java 8 by Oracle, but there's also a version 6 and a version 7 by OpenJDK. And if you take a look at this, so I'm looking at version 6, Here's some bash for you. So there is a jar file, ls-l. So these are backticks. So it is right below the escape key, lowercase. It is like a backslash, only it's an apostrophe, a back apostrophe. It's not a straight apostrophe, it's a back apostrophe. And it says, so I'm doing an ls-l, so I give it a directory or a path, directory or file path. And in this file, gre.dir.txt, I have the path, the absolute path to what's called the runtime classes, boot class classes for Java 6 for the Open JDK. So if I do that, you can see that it shows me a long listing of that jar file. And let's just, instead of doing a long listing of it, let's jar tvf. Bunch of them in here. So we'll pipe it to less. And you can see, so com.sun.accessibility.internal.resources, accessibility class, and so forth. There are a bunch of classes in here, and let's just kind of play around this a little bit. So you can see the package is based upon the nesting of it, and then each of these classes are dot classes. They're compiled. Literally Java programs that are compiled. And we'll get out of that. So let's, instead of piping it to less, let's pipe it to grep minus I. So I'm doing a listing of all of the boot class path classes for the JVM. So every time that you invoke a Java command, it loads, there is a boot class path loader, and it loads all of these classes. Grep minus I for java/lang/string.class. All right, so there is the string class, string.class, and it has 21,024 bytes in the .class file for class. So java.util.hashtable .class. So there's the hash table class from Java util and so forth. So all of the API classes are in here. And how many of them are there, right? I've mentioned in class several times that there's a buku, a large number of classes that get loaded. Well, there's also a Unix command, it's for word count. Pipe it to word count-L. And that tells me the number of lines in that, right? So this is the number of classes that exist in this jar file, rt.jar. RT, of course, stands for runtime.jar. So you can see there's 17,410 classes that the Java runtime environment loads when it starts up, 17,410. That's a lot of classes. So at runtime, there's a storage structure that represents the details of classes. So not only does it get the code cells for the classes when there are code cells for it, it actually creates a runtime structure for it, and that runtime structure is actually rooted at this class called java.lang.class. And java.lang.class, let's see if I got it bookmarked. Now I know where I can find it. let's go to the API reference for Java lang class. I tell you, I have more trouble with this particular mouse. So java.lang.class. So the type of the class modeled in this class object, for example, type of string.class is class of string, right? So if I want to look at the class object, so the class has an instance. There's an instance of the class for every class that gets loaded into the Java runtime environment. So those 17,410, I think, were lines in rt.jar are all separate .class files. And as the Java runtime environment starts up, it loads and creates a class instance for all of them, and builds that in the heap. The methods that are available, so if I get the instance of a given class, I get the class instance for a class like Java language string. I can find out lots of different stuff about it. So these are static methods to get the class itself, right? Static class, so a for name. So I get a class dot for name, and then the string name of a class. And if the class is not already loaded, so if I've written a class and it's in my class path, but I didn't load it at runtime, I haven't imported it or referred to it in the code, then in fact it will actually load it at runtime based upon a string. And we'll see an example of that in just a couple of minutes. There is, in addition to all of these things, there are methods for getting, here we go, get the declared fields. So there is a class called field. So if, for example, remember the user class that we've looked at before that has, or let's check the media description class. The media description class has an author and it has a media type. All right, all of these things are fields, the file name for it. Each of those fields, if I get declared fields, I could get an array where each element in the array is a field object that describes all of the fields in the class media description. And the same thing for methods. So get the declared methods from a class. Here are all the methods that exist within a given class. Declaring class, the enclosing class. I mean, there's just all kinds of different information you can get about a class. In fact, you can actually cause the Java runtime environment to compile a Java program to generate a class file and then load that class file and then create an instance of that class. That's how dynamic the Java language is. Okay, so enough of that. Let's go back to here, and let's execute this thing, reflection.jar. So this is in the class notes 5.b3, and what this is going to do is to use these class and field and actually methods, method class, to reflect and tell us information about a class. So I think I've already downloaded it, but let's make sure. Examples, that's it. The most recent one. So extract it, and the name of the project directory is reflection. When it's extracted, there's an ant build file, and then in the source directory, there are actually some weird classes that are in here. These are classes that were done by students in a CST 200 class a long time ago. and I ended up implementing them myself. So here is the one we're looking at, reflectclass.java. It's the main program. The rest of these things, actually, there's an interface and a base class. So let's see if I remember how this all works. Food exception is a class that extends exception. Food store, the intent is I'm going to have some kind of food and I'm going to create a storage of that food. I think cookie jar extends food store to provide for storing cookies, and coffee machine extends food store to store coffee. So as a part of food store, there are methods for determining the flavor. So you might have chocolate chip cookies and peanut butter or oatmeal or whatever, and Irish coffee and so forth. And then store operations is an interface. And not a class. I think food store implements the interface store operations. And we'll find out here. I want to show you something else about this. So when you do ant, here are the targets: prepare, clean, build, Javadocs, and targets. Create Javadocs. So I've gone in and made extensive Javadoc comments in each of these source files. You might want to look at one or more of them just as a pattern of how to create good Javadoc comments. So not only is the class header commented, but there's also comments on all of the methods as well. So if I say ant, here, make sure nothing there, ant create Javadocs. It's going to create for me a set of HTML files that look just like the Java APIs, but they're for this this particular package. So there's nothing magical about Ant with this. With the JDK, when you download a JDK, you get a tool called Javadoc. So far we've looked at serial version UID as one of the tools. We've taken a long look at Java. Java-C jar command as well. We've also looked at the RMI compiler. When we did RMI, that's RMI-C. Right, so all of this is just Ant using the underlying tools that are already there. And now after doing create Javadocs, we now have, we've compiled it, and we also have a docs directory. And you can see in the doc directory is a bunch of HTML files. So let's open up the base of it, and iceweasel doc index.html. So here it is, and let me boost it up so we get a good, so it looks just like the Java API. This is how the Javadocs are created. There's a Java implementation of all of the base classes. And these show me two different packages. One is SER321, and that's the reflect class, the main class. And if we look at the method summary, you can see there's a main method and print class header, print constructor of class, print field of class. So these are all methods in reflect class. And then in our countertop thing, these are the coffee machine, cookie jar, food store. So these are three classes. We have an interface for store operations. And if we look at that interface, all known implementing classes, coffee machine, cookie jar, and food store implement it. And then it gives, so there are directives that you can put into the Javadoc comments. Let's just take a look at store operations. All right, so the package is SER321 countertop, import Java util star, probably not the right thing to do, but that's the way it is. And then public interface store operation. So here you can see the directives The P is a new paragraph. So let's just kind of look at, we are at, yeah, purpose, an interface for countertop classes. All right, an interface for countertop classes, purpose. And notice that purpose, even though they're on separate lines in the comments, they're on the same line here. Purpose and interface for countertop classes. And then the P is HTML, so give you a new paragraph. So you can see a paragraph separating, and then SCR 321 Principles of Distributed Software Systems. So there's that line. Actually, these C's all go down at the bottom here. C also, so these are all hot links. SCR 321 homepage, coffee machine. So these are, you can do a C to a web page, or you can do @C to another Javadoc. SCR 321 countertop coffee machine. And you can see @version provides for me in bold the version, and then whatever I provided for the version. So the Javadoc comments, and then the other thing I guess we mentioned for methods, @parm is the Javadoc for given parameters. So @parm flavor is documenting that parameter, is a string specifying the flavor to add. So let's just take a look at add, the add method. If you go there, under the add method, flavor, under the parameters, flavor is a string specifying the flavor to add. Notice add is bold because I included the HTML start bold and stop bold, right, as part of the Javadoc comment. So you can see that Javadoc comments provides you the ability to comment your code in such a way that you can generate Javadocs that help, especially for interfaces, right? When you an interface, generally you don't create an interface unless you expect someone else to use it, and it always makes sense to have detailed comments for it. So there's some examples of that, and Ant within the Ant build.xml. We're already there. Create Javadocs. Javadoc, so there's a tag, predefined tag in Ant called Javadoc that uses the Javadoc tool, and you provide some attributes, class path, give it a class path, and then tell it the files that you want to be run through the Javadoc, run through Javadoc. And that's how we ended up getting all of the packages defined for us, and each of these different files processed to generate HTML files for them. Okay, so that's one of the things that's in here, but that's not anything to do with execution. It's just to show you, if you haven't seen before, the right way to comment your code and to provide documentation so that others can use your code in an appropriate way. So now let's execute it before we play around with it. So Ant. And here's how we get it to run. Java CP classes SCR321Reflect class, and it's going to ask us to provide some input for it. So let's just do a copy paste here. Okay, so remember what this program is going to do is I'm going to input a string. It's going to ask me to enter a string. All right, so this is, the first one I'm going to enter is one that has not been loaded yet. So let's paste it, SCR321 countertop coffee machine. And as long as the class path for the runtime environment for the Java command has in it SCR321 countertop coffee machine.class, it'll load it, and it will generate, it'll go through it'll get the class object for the loaded class, and then go through all the methods that class defines. So SCR321 countertop coffee machine extends SCR321 countertop.foodstore, and then it shows the different methods. So there's a public method that returns a string, and the name of it is brew flavor. and brew cups available is an int. And then here's the constructor for it. SCR321 countertop coffee machine that takes 2 arguments. One of them is a string, probably the name of the coffee machine, and the other one is an integer, probably how much coffee, I don't know. And then brew remaining in units must be cups. And then brew flavor, returning a string. And brew is to takes in a string and an integer, right? So brew so many cups of such and such a flavor. So let's also look at what was the base class food store. So here you can see, right? So this is getting the class, and then following getting an array of the methods and printing out all the information about those methods. And a method has subordinate to it a set of parameters, so you can find out the parameters for a given method and the types of those parameters. So this code is actually going through all of that in order to do it. So far, the classes that I've entered are classes that it had to use a class loader in order to load them, and then after, as a part of getting the class. Let's also enter java.lang.string, right? One of the predefined classes. This guy's already been loaded, and you can see there's a bunch of stuff in Java lang string. So I go through, so here's one of the substring methods, another one of the substrings, last index of a given character, and so forth. So you can see each of the different methods that are defined, whether or not the method is public. In this case, it's a static method, returns an int. Private, here's a private method that last index of supplementary. That's not one that users of the string class can call. Public Java language string intern, and so forth, right? So all these are printed out. So let's take a quick look at the code that does this. I think hopefully you get an idea of what it does. So here's the main method, and it creates an instance of this class. Input stream reader, right? So this is going to be a buffered reader that reads in the line. System out print class name or exit. So I read in a line. If string equals exit, then break. Don't tell Richard I do that. Class loader dot system get system class loader dot load class of string. All right, so I read in java.lang.string. And if it's already loaded, then it won't load it. But if it's not loaded, then it will load it. And then class my class for name, and then that string. So this is getting me a class object, an instance of the class, an instance of the class called my class. And now I'm calling my reflect, print class header, print field of class, print constructor of class, and print methods of class. All right, so this is going, calling the different methods above. So I'm passing them a class object, and that class object, so here you can see, we'll just look at one of them, print methods of class. It takes in an instance of a class, and it asks, give me the declared methods of that class. So I get an array of methods, and now for each of the methods in the array, string header, I get the modifiers for the class, and so forth, right? So this is building a string based upon the modifiers. So if we go back and look at string, where did I enter string? It's a long one. So what it's doing is building this public class. There's the name of the class, what it extends, and so forth, right? So that line of output is being generated by this guy. All right, system.out.println, the header for the class, and then visibility mode, so forth. So I'll let you take a look at the code in more detail. The main thing, the important thing here is it's using it's called the Reflection API, and it's primarily based at the class. And from that class, you can get all kinds of information about a class. So this example program shows you how to load a class if it isn't already loaded. All right, if it's not already referred to elsewhere in the program, it won't already be loaded. So here's a way to load a class, and then after I've loaded it, give me the class instance of it, and now reflect about the different information on it. So this runtime environment that Java has is actually pretty extensive. Okay, so now there's a diagram here. We'll just finish with this thing. So here's kind of a picture of the runtime storage, and it's intended to, it's reflecting this guy. So here is a very simple, this isn't even Java, it is, I'm not sure what it is. So I've got a class, the name of the class is main, and it extends object, and here's the body of it. Define a method main that returns a bool, and here's the code in that method main, all right? This is a new main, hello world.putLine, and then return true. All right, so main returns a bool, and that bool is going to be true. And the main method, all it does is create a new main object, and then it sends the string hello world a message to print itself, to putLine. So the runtime environment for that program is shown here in the following way. We have our activation stack only has one frame on it, and these are T's are intended to be temporaries. So the code cells actually reflect what would be the code cells for that code up above, and then all this other stuff over on the right-hand side is the heap. All right, so there are references. So the variable this would be on the activation frame, and it would be referring to an instance of an object that had been created, and it's an object for main. All right, and it has a parent which is an object. So in this case, the object doesn't have anything. All right, so in fact, when I create an instance of a class that has a parent that extends another class, which everything does unless it's an instance of the object class in Java, there's a whole parent structure. And there's no guarantee that the implementation of a Java runtime environment literally separates these things out or glues them all together into one object on the heap. But nevertheless, if main extends object, then there will be on the heap a storage area for all of the fields of main, together with all of the fields that are defined inside of the object class, an object of the object. All right, so, and then I also have a string. So I have an object for string, and its value is hello world, and it extends object, string extends object. So in fact, there'd be an object instance as well. And then there are the class elements, right? So class for main. So this is the instance of the class, and here's the instance for main, and here's the instance of the class for string, and the instance of the class for object. So this is the reflective API that gets built when I load a class. All right, so when I load a class and get its class object, on the heap, we create objects for each of the reflection objects, class objects, method objects, field objects, and so forth. And then, of course, the code cells that cause it to execute. So I'm hoping that that gives you a little better idea of what a runtime environment looks like. You know, maybe it's not explicitly exactly as I've shown you here. Actually, I'd be very surprised if it was. But in fact, there are code cells, an internal representation of the code cells of the heap, and each of these different blocks or components that are on the heap, as well as the activation stack. I've only shown one frame on the stack, so if main called another method, when the put line method would be called, then in fact there'd be another activation frame put on the stack. So the other thing I haven't mentioned yet is this thing called a processor, and it's the thing that ties us to the next section and the next unit, and that is the notion of threading. So the processor is a virtualization of a machine that's able to execute instructions. And the processor has two different components. It has an environment component, which you can consider to be its data, and it also has an instruction pointer. So if you took CST 250, then in fact you looked at machine organization. And in machine organization, I'm sure you talked about a program counter. Well, this is the logical equivalent of a program counter for a high-level language. So the IP is an instruction pointer, which is pointing to one of these code cells. So the IP, the instruction pointer, has a value of 5. It's referring to, this is actually a call, dispatch T2 put line. All right, in addition, every instruction has to be executed in the context of some data environment. That's how we can do recursion, that's how we can do reentrancy, and that's how we can have threads. So we may have multiple threads using these same code cells, and the way that it all works is by the fact that there's a different data pointer. So for a processor, it has an instruction pointer and an environment pointer. When I create a new thread in Java, what I will do is create a new processor, instruction pointer, and environment pointer, and also put a new special method, it's called the run method, pop it onto the activation stack. And the environment pointer is always a pointer to not the top of the activation stack, but it's a pointer to its current location within the activation stack. So if I create 5 threads in my program, I'm going to have 5 different IPs and EPs that are active while those 5 threads are executing. And for each of those 5 threads, I have pushed onto the stack, the activation stack, a method, a frame for its run method. Okay, so that's what we get into in the next section. And that is multi-threaded programs, how we create them in Java, and what actually happens to them when we put them into execution. So I'm going to leave it at that for this unit, and that completes the unit on Unit 10 on runtime environments. The lab exercise is actually the same one that was introduced last time. There's no need to do reflection as part of solving this current problem. This is actually the download mechanism, and we're talking about the background, the threading that you'll have to create in your server as well as in the client as well. Okay, so this is background for that, and nothing directly is going to go into that lab exercise.